So we're going to start our 3.6 now, which is dealing with our absolute value functions. This is a very short section, and you've learned a lot about absolute value in Math 190, so it's really just a lot of review from that. Our two objectives in this section are being able to solve an absolute value equation and then being able to solve an absolute value function. And so we have some formal definitions here. Why don't I have a student read the first definition that I have in pink, and then maybe I'll have another student read the second part, which I have in blue. So pink, anyone? Go for it.
Absolutely.
Beautiful. And blue. Anyone else? Maybe from the back. Yeah.
Real number say the equation of form absolute value of A equals B with B greater or equal 0 would have both have solutions when A equals to B or A equals negative B. If B is less than 0, then the equation absolute value of A equals B has a solution.
Beautiful. Yeah, so the key takeaway is anytime you're dealing with absolute value, you have two potential cases. You have the positive version, and then you have the negative version. But from the start, if you have B is negative, and that left-hand side is all equal to positive, that will never, ever give you a solution because absolute value of any numerical value is always going to shoot to positive. It will never be negative. And so you'll have no solution there. So let's start off with our example 1. We have absolute value of 4x plus 1. Close absolute value minus 7 is equal to 0. Again, you want to hone in on two different cases. But before we go into the two cases, your first step is to get your absolute value all alone on one side. You want to isolate it. So when we do that, we end up with the absolute value of 4x plus 1 is equal to 7. Now you want to think of, okay, your two cases, your positive case and your negative case. So create your two cases. When your cases are created, you can drop the absolute value. So we have our positive case where you just drop everything completely and you're looking at 4x plus 1 equals 7. And then you have your negative case where you drop everything, but you want to multiply that right-hand side by a negative. So 4x plus 1 is equal to a negative 7. And then from there, you're just solving a linear function or a linear equation in this case. So solve for your potential values of x. Positive case, use inverse operations. We're going to subtract 1 from both sides. We can do that for the negative case as well. Kill 2 birds with 1 stone. And so now you're looking at 4x is equal to 6 for your positive case. For your negative case, you're looking at 4x is equal to -8. And then inverse operations again, we're going to divide both sides by 4. And so your two potential solutions are going to be x is equal to 6/4, which is reduced to just 3/2, or x is equal to -2. And then the last step is you're going to check. So, a sec. Yeah, so we have our last step, which is checking, because there are certain times where these solutions, one will work and the other one won't, or none of them would work. So how do we check? The first one, we literally just plug in 3/2 wherever we see x into the original. So we're looking at 4 as a fraction is just 4/1. So 4/1 times 3/2 is 12/2, which is just 6. 6 plus 1 is 7. Absolute value of 7 is 7. And 7 minus 7 is 0. So I'll try and write that last one. And then let's check for when x is equal to -2. So 4 in parentheses, -2 plus 1. Four times -2 is -8. -8 plus 1 is -7. Absolute value of -7 is +7. Minus 0 gives you 0. So both solutions work. Therefore, your final answers are x is equal to, put it in ascending order, so -2 goes first, and then 3/2 goes last. Yeah.
In the last part, you say that the absolute value is -7, +7. So in the first part, why you would say that the absolute value of +7 is -7, +8 is 42.
Well, it's the absolute value of +7 is 7, and the absolute value of -7 is also 7. Because anytime definition of absolute value is distance away from 0. And I can create maybe another slide. Distance is always positive. Distance away from 0. And then we have distance is always positive. So if we look at this from a number line standpoint, we have 0. And then if we look at an example, okay, the absolute value of -4. 1, 2, 3, 4. This is our -4. How far away is -4 from 0? 4 units. So the absolute value of -4 is +4. But let's say we were looking at the absolute value of just +4. How many units away are you from 0 here? Also 4. So you're always shooting out a positive version. Was that your question? Yeah. Yeah, so whether it's negative or positive inside those absolute values, it's always going to spit out a positive. Whereas the definition of opposite numbers is different. That's what I think you're thinking of. It's just opposite sign multiplied by negative. So -4 is opposite of 4. 4 is opposite of -4. This is different from absolute value definition. So yeah, this was the solution for that example one, -2 and 3/2. I do want to finish this up and then I'll give you your break because it's only a few minutes longer. So just bear with me and you'll get the full 20 minutes break in a moment. So our second objective is graphing an absolute value function. Again, our general function of any absolute value is f of x equals the absolute value of x. And it's one of our famous functions, our toolkit functions, so it's good to know what it looks like. It's that V representation. And really what I was talking about on that previous slide that I made, distance away from 0, distance is always positive. Your y values are always going to end up shooting to be positive, but you can have negative x values, right? Absolute value of -4. You can have positive x values, the absolute value of +4. And so absolute value is really represented as a piecewise function because you're dealing with your negative x values and you're also dealing with your positive x values, but your y values will always remain positive. And so how do we represent this as a piecewise function? We have both our positive linear function and our negative linear function when our x values are both negative and positive. And then our domain for any absolute value of x without any transformations. We have no restrictions for x, but we have that restriction for y. Y can only be 0 or positive. X, all real numbers. And then this is the, yeah.
Yeah.
Okay, cool. And then this is the graphical representation, a little bit more detail oriented. You can clearly see that your lowest Y value is 0, whereas there are no restrictions for your X. So now let's sketch an absolute value that has a few transformations that take place. Notice we see a horizontal shift, we see a vertical shift, and then we also see a reflection, right? That negative in front is a reflection across what? Your X or your Y axis? X, good. And if it's a reflection across your x-axis, is it going to be a vertical reflection or a horizontal reflection? Vertical. All done. So, actually, I keep sketching out the thing, but I know I have a screenshot from my photos there. Much better. So, I will sketch out my toolkit on the same graph so you can see the transformation take place. Our horizontal shift is going to be what? I should use different variables. We're going to make the toolkit function g of x. We have our horizontal shift is 2 units to the, yeah. And our vertical shift is 3 units. Vertical is up or down, right? 3 units up. And then we already spoke about our reflection. Reflection across x-axis, aka vertical reflection. So always use that vertex as your base. You're going 2 units to the right, and then you're going 3 units up. 1, 2, 1, 2, 3. And then you're doing a reflection across your x-axis. So this purple point is being reflected across the x-axis. So we have 1, 2, 3. So this is where your point goes. And we want to do this for at least 3, maybe 4 points. So we'll do the same with this guy over here. Again, 2 units to the right, 3 units up, 1, 2, 3, and then we're reflecting that across. So it's really 1, 2, 3, 4. Once you get the vertex in and you know that your absolute value is now going to be an upside down V since of that vertical reflection, then it's pretty straightforward to just sketch out the other points because it's just going in that diagonal format. And then you can connect the dots. That's it. Don't forget to write out and label your function. And then we need to state, it says label the intercepts on your graph and state the domain. So do we have any x-intercepts here? No, we don't. But do we have a y-intercept? Yeah, our y-intercept is over here. So we're just gonna write y-intercept, and then the coordinate point for that is 0, -5. And then our domain, what's our domain? Any restrictions? Nope, so it's gonna be all real numbers, -infinity to +infinity. What about our range? Yeah, exactly. We have -infinity to -3 hard bracket. And we're done. Yeah.
So. Shifts. Put in that specific order, so like horizontal shift, vertical, and then reflection.
Very good question. You don't have to. You can do the horizontal or the vertical reflection first, and then the horizontal, and then the vertical. Yeah. You'll end up at the right point either way. Yes. How did I shift 3 units? That's because of the reflection that took place. So, it is a vertical shift up, but then it's a reflection across your x-axis. So once you move this graph up, you're flipping it across your x-axis, so then it comes down over here. Yeah. Bless you. And so now we're tying this into the whole even or odd from our previous section, stating, okay, is absolute value of x an even or an odd function? We have that it's symmetric about the y-axis, right? From our visual. Reflects across the y-axis perfectly, which means it is even. And then they also put in that general equation of any absolute, which contains your horizontal shift, where that C is, your vertical shift, where that K is, and then that A value. If A is negative, then we have a reflection across the x-axis. If A is positive, then no reflection takes place. And then if A is a number, that sort of goes into vertical stretching and compression, which we'll lightly touch upon soon. And so that brings us to our, I believe, last slide for this section and our last example, being able to sketch this graph, which has, once again, a horizontal and a vertical shift. And now we have that A value, which isn't negative. So do we have a reflection here? No. But we have this vertical stretch that's taking place. So it'll be good to see what that looks like on our graph. Also, it's important to know how to manipulate through transformations. However, let's say you forget all of the rules and stuff. Never underestimate the ability of building a table and just choosing good x values, plugging it into your formula and spitting out the y values and then just plotting it. You'll get full credit that way as well. And actually, why don't we do it for this problem so that you can really see what I'm talking about? Can just literally create an X and Y table. Does it help knowing the vertex? It does. But you don't have to know it. So why don't we choose, let's see, I'm gonna get some negative values in here. -1, let's go actually up to -3 because of this horizontal shift. So -3, -2, -1, 0, 1, 2. If we need more, we can add more. Maybe let's add in 3 as well. So we have -3 minus 3 gives us -6. Absolute value of -6 is +6. 6 times 2 is 12. And 12 minus 4 gives us 8. That's our y. Now let's look at -2. -2 minus 3, -5. Absolute value is +5 times 2 is 10. 10 minus 4 is 6. -1 minus 3 is -4, shoots out +4 times 2 is 8, minus 4 is 4. 0 minus 3 is -3, that shoots to +3 times 2 is 6, minus 4 is 2. 1 minus 3 is -2, shoots to +2 times 2 is 4, minus 4 is 0. 2 minus 3 is -1. -1 absolute value is +1 times 2 is 2, minus 4 is -2. And then we have 3 minus 3 is 0. Absolute value 0 is 0 times 2 is 0, minus 4 is 4. Did I do the math right for this one? Let's see. Yeah, I did too. Okay, cool. Right, let's plot this. -3, 8.
Oh, only like 3 is it?
Yeah, thank you. I was like, something doesn't look right. Okay, so -3, +8. Here. -2, +6. -1, +4. 0, 2. 1, 0. 2, -2. 3, -4. We need the vertex. Let's see. Let's put in some more values. Let's do negative. We did -8. then we would have negative 11 times 2 is negative 22. Sorry, negative 11 absolute value gives you positive 11 times 2 is positive 22. Minus 4 is positive 18. Should go up even more. So our vertex is actually going to be over here. We just haven't hit it yet. All right, let's do maybe positive 6. 6 minus 3 is 3. Absolute value of 3 is 3 times 2 is 6. Minus 4 is 2. Yeah, all right, we're good. So 6 comma 2, which means I have a feeling this is a vertex. So let's put in, let's see, 4 and 5 as well. So 4 minus 3 is 1. Absolute value of 1 is 1 times 2 is 2, and 2 minus 4 is negative 2. Yep. So 4 and negative 2. And then you can see that with the reflection, our 5 is going to go right over here, right? 5 and 0. 5 minus 3 is 2. 2 times 2 is 4, and 4 minus 4 is 0. Still helps to know your toolkit function, that it's going to be a V-shaped. So you really want to hone in on that vertex. And our vertex, I'll show you how to easily get it in a moment, but our vertex is 3 comma negative 4, which if you look at the general equation of an absolute value function, we have f of x is equal to a. X, they use C and K, so I'll keep it in those, but some textbooks use H and K, and your H and K are is your vertex, but in this case, they have it as your C and K. Yeah. So much easier, right? So in this case, our vertex is 3 comma negative 4, which is exactly what we had over here.
Like this one for O.
Yep. Yeah, so it'll save you time too. Because once you have your vertex, you don't need all these points. You just choose 1 or 2 points to the left, and then 1 or 2 points to the right, sketch, and then you're done. And so don't forget to label your graph. F of x is equal to 2, absolute value x minus 3 minus 4. What's our domain here? Domain, all possible x values. Yeah, all real numbers. And then what's our range? Hard bracket, negative 4 all the way up to infinity. That's good. All right. Yeah. Thank you. Intercepts. We have 2 x-intercepts. We have one at 1 comma 0, and then we have another one at 5, 0. And then our y-intercept, we only have 1 at 0, 2. Where it intercepts your y-axis. And then we're done. So this concludes our section 3.6. And then our next section is going to be inverse functions, but I'm going to give you guys a bit of a break.